Isocyanates are a highly reactive class of organic compounds containing cumulative double bonds with the formula R-NCO. The reactivity of isocyanates is governed by the electron-deficient nature of the central carbon atom, which is susceptible to attack by various nucleophiles, whereas the oxygen, and less commonly the nitrogen, reacts with electrophiles. Isocyanates are a member of the class of functional groups suitable for chain growth polymerization, which are cumulated double bonds of the general form X double bond Y double bond Z, in which the central atom is carbon. The three most common cumulated double bonds, which are isoelectronic with each other, isocyanate, alene, and keton. The double bonds share a central sp hybridized carbon atom, and thus the neighboring pi bonds are not conjugated and are orthogonal to each other. The orthogonality of the double bonds in cumulated systems provides an exciting opportunity to access different polymer backbones from a single monomer, provided the regioreactivity is controlled. Synthesis of isocyanates. Many isocyanate-containing compounds are commercially available. The most common methods for their synthesis are reaction of amines or amides with oxalyl chloride, reaction of olefins, halides, acid anhydrides with isocyanic acid, Curtius rearrangements, and phosgenation of amines, the latter of which is used commercially. Isocyanate is predominantly produced via the phosgene process, which currently holds a paramount status in industrial isocyanate production. Nonetheless, concerns arise from the toxicity of phosgene and the corrosiveness of hydrogen chloride, posing safety hazards. The synthesis of isocyanate using non-phosgene methods represents a promising avenue for future development. Isocyanate is the key raw material for the production of polyurethane. Due to the extreme toxicity of phosgene, the synthesis method of isocyanate is gradually changing from phosgene to non-phosgene. Isocyanates reactivity. Isocyanates undergo reaction at the carbon atom with compounds such as alcohols, amines, water, mercaptans, and carboxylic acids. These reactions result in various carbonyl-containing functional groups used in the synthesis of both small molecules and polymers. Aromatic isocyanates self-react to form dimers, uretidinidiones, at low temperatures and trimers, isocyanates, at high temperatures in the presence of acidic or basic catalysts. Isocyanate functionality is highly reactive toward proton-bearing nucleophiles. The reaction occurs by nucleophilic addition across the carbon-nitrogen double bond. The basis for the high reactivity of the isocyanates is the low electron density of the central carbon because of the resonance structures of isocyanates. Aromatic isocyanates are generally more reactive than the aliphatic isocyanates. The presence of electron-withdrawing substituents on the ring of aromatic isocyanates tends to increase reactivity, whereas electron donors decrease reactivity. Isocyanates for polyurea and polyurethanes. Isocyanates are monomers for polyurea and polyurethanes. These well-known polymers are produced by step-growth polymerization of diisocyanates and diamines or diols, and the products find use as coatings, adhesives, foams, and sealants. Bayer et al. First discovered polyurea in 1937 by reacting an aliphatic diisocyanate and diamine, and later polyurethane was obtained by reaction of an aliphatic diisocyanate and glycol. Many difunctional isocyanates, such as toluene diisocyanate (TDI) and hexamethylene diisocyanate (HDI), as well as polyfunctional isocyanates such as TDI, trimethylolpropane, and the isocyanurate trimer of TDI, are widely used in the polymer industry. In addition to bulk and foamed polymers, polyurea capsules can be prepared by interfacial polymerization in emulsions. Alternative to the step-growth polymerization of multifunctional isocyanates and multifunctional amines or alcohols. The isocyanate functional group can be used as a monomer in chain growth polymerizations, yielding polyisocyanates with a backbone of R-NCO repeat units in which the nitrogen atom bears a pendant R group. Isocyanate chemical structure. Isocyanates are generally classified into two broad types, aromatic and aliphatic, which describe their backbone structure. While monofunctional isocyanates exist, they are not generally used in the coating space except as moisture scavengers. Generally, diisocyanates or polymeric isocyanates are used for commercial applications. Polyisocyanates, or polymeric isocyanates, have a functionality of over 2, usually 3 or higher. To combat the volatility of isocyanates, polymeric forms are produced. Not only are they safer to use, but the increased functionality of polymeric isocyanates raises the cross-link density of the coating, all other raw materials being equal. This leads to better chemical resistance and higher hardness, but can decrease flexibility. Isocyanates, D, and polyfunctional isocyanates are commonly used as monomers to make various polymers, such as polyurethanes. The reaction of diisocyanates, or polyisocyanates, with polyols, molecules containing at least 2 free hydroxy groups, produces the corresponding polyurethanes. Among those diisocyanates, toluene diisocyanate, TDI, 4,4-diphenylmethane diisocyanate, MDI, hexamethylene diisocyanate, 8-HDI, and isophorone diisocyanate, IPDI, are commonly used to produce polyurethanes. Oligomers and prepolymers of isocyanates with low molecular weight are derived from existing or new isocyanate monomers and are widely used as feedstocks in the polyurethane industry. Aromatic isocyanates. Aromatic isocyanates are isocyanates where the NCO group is directly attached to an aromatic ring. Aromatic isocyanates are used in applications where color stability and UV resistance are not necessary. Consequently, aromatic isocyanates are often used to produce polyurethane systems that will be used in indoor applications for primers, foam, and elastomers. Aromatic isocyanates, such as toluene diisocyanate, TDI, and methylene diphenyl diisocyanate, MDI, are characterized by their aromatic ring structures. Due to the higher volatility and worse health profile of TDI versus MDI, TDI is not used in self-leveling coatings. However, these isocyanates are widely used in the coatings industry due to their several advantageous properties. Fast curing. Aromatic isocyanates react quickly with polyols, leading to faster curing times. This makes them ideal for applications requiring quick turnaround times. Mechanical properties. Coatings formulated with aromatic isocyanates exhibit excellent mechanical properties, including high hardness and abrasion resistance. This makes them suitable for industrial and heavy-duty applications. Cost-effectiveness. Aromatic isocyanates are generally more cost-effective than their aliphatic counterparts, making them a preferred choice for budget-sensitive projects. However, a notable drawback of aromatic isocyanates is their poor resistance to UV radiation. Exposure to sunlight can cause coatings using aromatic structures to yellow and, in some instances, degrade over time, limiting their use in outdoor applications where aesthetic and/or long-term performance are critical. Aliphatic isocyanates. Aliphatic isocyanates, such as hexamethylene diisocyanate, HDI, and isophorone diisocyanate, IPDI, feature aliphatic chain structures that impart different properties to the coatings. UV stability. One of the primary advantages of aliphatic isocyanates is their excellent resistance to UV radiation. Coatings made with aliphatic isocyanates maintain their color and gloss over extended periods. making them ideal for outdoor and high-visibility applications. Durability. Aliphatic-based coatings exhibit superior chemical resistance and weatherability, ensuring longevity in harsh environments. They are often used in automotive, aerospace, and architectural applications where durability and appearance are paramount. Versatility. Aliphatic isocyanates are versatile and can be formulated to provide a range of finishes from matte to high gloss, enhancing the aesthetic appeal of the coated surface. The main disadvantage of aliphatic isocyanates is their higher cost compared to aromatic isocyanates. Additionally, they typically cure more slowly, which can be a consideration in time-sensitive projects. The choice between aromatic and aliphatic isocyanates depends on the specific requirements of the coating application. For instance, in indoor industrial settings where UV exposure is minimal, aromatic isocyanates are often preferred due to their cost-effectiveness and robust mechanical properties. On the other hand, for applications demanding high UV stability and aesthetic durability, such as exterior automotive parts, architectural elements, and outdoor equipment, aliphatic isocyanates are the go-to choice. Understanding the differences between these two types of isocyanates enables formulators to design coatings that meet the precise needs of various industries. By leveraging the unique properties of aromatic and aliphatic isocyanates, manufacturers can create high-performance coatings that provide long-lasting protection, durability, and visual appeal. Blocked isocyanates. Urethane linkage is thermally reversible to alcohol and isocyanate. Depending on the nature of the alcoholic substrate and the presence of active hydrogen compounds, this reaction can be utilized to mask or block isocyanate functional groups. Blocked isocyanates are stable in the presence of active hydrogens at room temperature, but unblock to liberate free isocyanates at elevated temperatures. Some commonly known blocking agents are oxime and caprolactam. Many of these blocked isocyanates are used in specialized coatings and adhesives. In conclusion, both aromatic and aliphatic isocyanates play vital roles in the coatings industry. Their distinct chemical structures and properties offer specific advantages and limitations that make them suitable for different applications. Selecting the appropriate isocyanate type is essential for optimizing the performance and longevity of high-performance coatings. While isocyanates are valuable in industrial applications, they do pose notable health risks if mishandled. These risks primarily arise from skin exposure. Chemicals with low vapor pressures, like aromatic isocyanates, can still lead to significant exposure risks through skin contact. Contamination from solvents, equipment, or surfaces can be hazardous. Respiratory sensitization. Exposure to aromatic isocyanates can lead to respiratory sensitization, making it crucial to limit inhalation exposure. Sensitization can result in symptoms similar to asthma, including difficulty breathing, chest tightness, and wheezing.